So at some initial time 0, we're going to come up with a contingency plan, right? So what do we mean? We're going to solve this optimization problem given our current information, and we have a consumption savings problem, right? So that means when I'm deciding about how much to consume today, I'm thinking about how much I'm saving at the same time, which means I'm thinking about how much I want to consume tomorrow. But we have an infinite number of periods, so thinking about how much I want to consume tomorrow is also thinking about tomorrow's saving, which is thinking about consumption the day after tomorrow, which means I'm thinking about the savings the day after tomorrow and consumption the day after tomorrow. So I'm thinking, when I decided how much I'm consuming today, I have an idea about how much I'm going to consume out to infinity. And the way to think about this is, well, I have a plan. I'm going to spend this much money on lunch today, so I'll have this much money left over so that tomorrow I can do this. I can go have coffee with my friends, and in the evening maybe go to the club, right, and dance, right, and on some money so that I can have lunch on Sunday with my parents, right, and then I don't know, go to the movies in the evening with my friends, right? But then, so that's my contingency plan. So that's how I decide how much to consume today, right? I have all these things I know I want to do this weekend. I calculate how much they cost, and then I have this much money left over today, so that's what I'm going to have for lunch, right? That's roughly, I think, what we do intuitively, even if we don't do that for every single activity. But that's kind of how we think. Now, tomorrow comes along, and the club is closed. Oh, well, so now I can't go to the club with my friends. So that means the money I would have spent maybe on a fancy cocktail or whatever, I'm not going to spend on that. So now I have, this changes my decision. If I would have known that today, or if I would have known today that the club was going to close tomorrow, I wouldn't have saved money to go to the club tomorrow, and I would have had a bigger lunch today. But I didn't know that. I didn't know that until tomorrow. So what we're doing is we're going to come up with a contingency plan. Today, given all the information we have, we're going to come up with our best plan. When tomorrow comes and I get new information, like the club is closed, I can and of course will change my plan. I'm not going to, I decided yesterday I was going to spend money at the club on a drink, so I'm going to spend money at the club anyway, even though that doesn't make any sense. Of course we'll change our plans when the world around us changes. So we're going to solve this problem at t equals 0, and then we're going to solve this problem at t equals 1. We're going to re-solve the problem again at t equals 2. Every period, all the time, we're re-optimizing. Right? That's what we're all doing too, right? When should I go to sleep? Oh, I wanted to continue watching that video, but I know at 9 o'clock I've got to be here. Right? You're always optimizing and rethinking things. So at any time t, we're going to face then the problem of re-optimizing. So using the information at time t, we're going to form the expectation of our lifetime discounted utility continuing forward. Right? And at period t, I'm not going to discount. Right? So the beta to the power of s, we put the power of 0. So this would be u of c t plus s n t plus s. And this is going to be subject to the budget constraint we've just determined, p t plus s c t plus s plus q t plus s b t plus s is less than equal to b t plus s minus 1 plus w t plus s n t plus s minus t plus s. I'm saying this plus s a lot. this notation is kind of cumbersome, which is why you'll frequently see it written like this, and just from the perspective of t equals 0 at the beginning of time. And then all these plus s's disappear, and we can also index with t to look forward. But it can be confusing when you take derivatives, and especially with the next part that we're going to do when we get this consumption Euler equation. Remember, guiding our consumption rocket ship through space. The importance of this conditional expectation can get lost. Right? Okay. So let's write the Lagrangian. And the Lagrangian is, let's start at period, right? We have expectation t of, and we have our utility function at period ct nt minus lambda t times then pt ct plus qt bt minus bt minus 1 minus wt nt minus tt. Oh, yeah, plus tt, thank you. Yep. Thank you. Plus tt. And plus beta times utility consumption t plus 1 and t plus 1 minus lambda t plus 1 pt plus 1 ct plus 1 plus q t plus 1 b t plus 1 minus b t minus w t plus 1 n t plus 1 plus t plus 1, and so on and so forth. All right, we start to write writing this in a sum is, it kind of hides the fact, right, of how much is in here. It helps to, this is what I call to telescope out the Lagrangian. We could write the Lagrangian also in the sum notation, but it's sometimes then easy to overlook what happens across periods. So the reason why we say telescope out, has anyone ever seen any of these Pirates of the Caribbean movies with, what's his name, the actor? I can see Captain Jack Sparrow, played by, what's his name? Captain Jack Sparrow by Johnny Depp. Johnny Depp, right? He's the captain. He's always walking around like this, doing funny stuff. Yeah, a pirate. Arg, arg. They had telescopes, and the way those telescopes worked is you could stretch the telescope out so you could see. Right? They would give you distance between the lenses so you could see far, and then when you needed to put it away, you would collapse it down and put it in your pocket. This is like a collapsed telescope. Very useful, very convenient for putting into your pocket. Not so good for seeing what's going on. Right? So really, I don't know, you've got the all right, that's that kind. And we can take this same part here. Right, and we telescope, we pull it out. And so now we can see what's going on. That's where this phrase comes from. And so now I'm going to come up with a contingency plan, you can think, right? I'm going to think about how much to consume today, how much to consume tomorrow, and so on to figure out what's going on here. But we can just, for now, write down the t variables, right? And know that we're going to re-optimize again in the future. So let's take the derivative with respect to ct and set it equal to 0. And we have our expectation at time t of marginal utility from consumption. All right, we see CT shows up there and there. Minus lambda t pt. All right. Have a good weekend. Yeah, see you on Monday. So, but now we can think about, well, what do we know? Do you know how hungry you are? Let's check. Yeah, I know how hungry I am right now. I might not know how hungry I'm going to be tomorrow, but right now I know how hungry I am. Do I know how much lunch would cost at the canteen? Yeah. Do I know how much, how tight my budget is? Yeah. This is all things according to our condition. Right? I might not know exactly. Some people knew exactly how much money they had. Right? So we can write this, however, then directly as u prime of c, ct nt minus lambda t pt. Right? All variables here are known at t and are in it, right? The conditioning set for that expectation. Right, so the conditional, we're calculating these expectations conditional on knowing these variables. So it's conditional on them. So we know them exactly. So that must hold. We can do the same with labor. Right, and we get ET U of N, CT, NT. All right, so now we're looking at NT and NT. So through there, minus lambda t times minus WT. For the same reasons up above. Right? That's all known at time t. So we get then that U, N, CT, NT plus lambda t WT. And we can combine these, substitute out lambda t, and we get equation 10 on slide 9. All right, so we can write this as minus UN. I'm going to drop the arguments and just write it as gamma t over U of CT is then equal to the real wage. marginal rate of transformation, marginal rate of substitution. We'll practice again interpreting this, right? So step 1, as a bachelor's student, we can take derivatives. Step 2, as a master's student, we can interpret these. Yeah? All right, so what would the interpretation here be? Well, the real wage, this tells me how, or the rate at which I can turn time into consumption goods. Right, the nominal wage turns time into money, and the price level turns money into a consumption good. All right, we can also write this as right, and here we have the marginal cost. What does it cost me to work? Well, I'm going to lose. Right, it costs me the utility gain or the happiness from not working. Well, that's why we've got the minus in front of it. It costs me my leisure, which would be the negative. Right, if we think of, let me write this out. So if we, yeah. Yeah, yes, let me write that down. So let's think of, if we think of, let's call it LT is leisure, right? Free time, kicking back, relaxing, right? All that stuff. Then if we normalize our unit of time, right? So we have 1 day, 1 minus LT is that part of the day where we're not enjoying leisure. That's when we're working. Okay? So now we can think of writing our utility function, CT, and with leisure. And if we take the derivative of this alternative utility function, this would give us then the margin utility from leisure. So this would be the utility from 1 extra hour of sleep. Yeah? Well, this is equal to the utility of this other function, or the way we've written it, in terms of, in terms of NT, where now we substitute 1 minus L for NT for our labor. And now we take the derivative with respect to LT. We get the outer derivative. And the inner derivative is then simply minus 1. So this, this is the derivative with respect to this is NT. So N. So this is giving us exactly the margin utility from leisure. So what we give up when we work is we give up the happiness of that extra hour of sleep. Yeah? Why would we do that? Why would we get up early? Right? Because they pay us. Yeah? For this 1 extra hour, we get, X thousand dong. Why do we care about dong? I mean, they're pretty pieces of paper, right? And you've got, different colors and architecture and Ho Chi Minh, right? But what am I going to do with that? Well, I can trade that for a good, right? How many goods do I get per dong or per 1,000 dong? Well, I divide through by the price level. So if now I've forgotten again. What's broken rice again in Vietnamese? Kap tam? Kam tam? Kam tam. Right? If Kam Tam costs, let's make it 50,000 dong per serving, and I earn, let's say, 200,000 dong per hour, divide the 200,000 by the 50,000, divide through by the price, and this tells me I earn German. 4, 1, 2, 3, 4. I've been in Germany too long. I earn 4 servings of Kam Tam per hour. So this gives me the money per hour that I earn, divide through by the price, tells me how many goods I can afford to buy with the money that I earn. And then I multiply it with my margin from consumption, how much I value this in the margin, right? How hungry I am. So why am I willing to wake up an hour early? Right? I give up the happiness of being able to sleep in, but this allows me to get money, to buy goods, to satisfy my hunger. Right? This is straightforward, intuitive, right? Just break the pieces up. So that's why I like the marginal cost, marginal benefit way of interpreting these things. I think it's very clear. Here we have the rate at which we can turn time into goods. And this is the rate at which, according to our preferences, we would like time to be transferred for goods. Right? So this is giving us this indifference curve argument, right? Just like we saw the consumption savings model. And now we get the big one. And this is the easiest way to make a mistake in these sorts of models, which is why it was so important for me to telescope out. There was no reason to telescope out for these other variables, but now it's going to be very important. We're going to determine how much we want to save, how many bonds we want to buy. Okay? So, help me find our bonds BT that we're so I start my utility function today. Well, I don't get utility directly from bonds. Okay. They show up in my utility function. If I buy a bond today. Wait a second. I have BT minus 1 here. Can I choose how many bonds I bought yesterday? Can I choose today how many bonds I bought yesterday? No. I can't change the past. Like sometimes I really wish I could. I can't change that. I'm choosing BT today. Right? So it only shows up once, right? Trick question. Right, remember, we just saw a BT minus 1. Those are the bonds we bought yesterday. I wish I would have bought a lot of them yesterday because they are generating the income today. Right? How much Bitcoin should I buy today? Right? It's going to depend on the price of that. Man, I wish I would have bought the Bitcoin in the past. I'd be really happy. But why would I be interested in buying Bitcoin today? Because the Bitcoin I buy today is tomorrow going to be the Bitcoin I'm glad that I bought from the perspective of tomorrow's yesterday. What is tomorrow's yesterday? Today. So let's look at tomorrow and see if we can find tomorrow's yesterday. Right? Bond purchases today, BT, don't show up in the utility function. They show up BT plus 1, those are the bond purchases we're going to make tomorrow, BT plus 1. But here we go, BT. These are tomorrow's yesterday. The bonds we buy today, the whole reason why we buy them today is they give us something tomorrow. This is giving us a connection across time through budget constraints today and tomorrow. That's exactly what savings is, right? we give up something today, right? We buy a bond today, right? We buy a stock today, we buy Bitcoin today, and then tomorrow, right? The savings pays out, the bond pays out, we sell the stock, we sell the Bitcoin. We're trying to connect today to tomorrow. Yeah? Okay, so now let's take that derivative. Now that we've found our BT, right? And that's, I like that. I've never explained it like that. Today, I think it's really good. We're looking for tomorrow's yesterday, which is today. Yeah? Tomorrow's yesterday. That's going to make me happy the whole rest of the day. Okay. So first we're going to condition on today's information set. Then we have, doesn't show up here, the derivative is then minus lambda t, Lagrange multiplier, times qt bt, the derivative with respect to bt is then just qt. All right, then we go to the next period, and we have this beta, right? Anything that happens tomorrow is discounted. Waiting for tomorrow is not fun, we're impatient. So we get then here plus beta, and we have minus, or we can just write out, so minus lambda t plus 1. And the derivative of minus bt with respect to bt is simply minus 1. And now, notice, right, there's minus minus, we can simplify. Do we know how much the bond costs today? Do we know how much things cost today? Yeah. Lambda t, do you know how tight your budget is today? Yeah, we know that. Okay, so we get then minus lambda t qt, minus minus plus beta. And now lambda t plus 1. Do you know how tight your budget is going to be a year from now? No, do you? You might win the lottery. You might find $500,000 lying on the street. We don't know what our budget's going to look like a year from now. Right? We don't know exactly. The best we can do is form an expectation, and from today's perspective, we're going to use that expectation at time t. We don't know, right? If we connect this, right, with our right, it's related to how hungry we are. We don't know. I don't know how hungry I'm going to be tomorrow. Right? I don't know. I mean, it depends on a lot of things, right? But I don't know. Some days I'm hungrier than other days. I've not quite figured out why, right? Or then if we substitute in the equation we have here, that the derivative for optimal consumption for lambda, right, we're going to get u of c, let's see, t, right, 1 over pt equals beta consumption Euler or Euler equation, just like we saw in our consumption savings model. It's a little bit different. Why? we're trying to figure out whether or not we should buy a bond. So what does it cost us? Well, the price in dong is QT. So we have to pay, I don't know, 100,000 dong. Okay, well, what's 100,000 dong? Let's make it 105,000 dong. Yeah? Well, 105,000 dong is 3 meals at the canteen. And 105 divided by 35 divided by the price gives me the quantity. 3 meals at the canteen. How painful is this? Giving up 3 meals at the canteen? I'm very hungry. If you told me, Alex, no more eating today, no lunch, no dinner, less than 2 meals, that's painful. Yeah? So that's the cost of buying this bond. This is money that I could have used to buy food that would then have given me utility and would have stilled my hunger. What's the benefit? Well, it's going to